linear configurations of MOSFET amplifiers in common source configuration, in source follower and common gate configurations. We have also discussed um, non-linear amplifications like Class C, Class D amplifiers, Class E amplifiers, switching amplifiers, and then we have seen some differential amplifier configuration. Now, in all these configurations, if we consider the AC equivalent circuits, usually we have up to this point have ignored any effect of internal resistance, which is inherent within the transistors. That those are, for example, we have not included in the AC equivalent circuits the junction capacitances, which are due to the reverse biased source and drain capacitances in between the body of the transistors. Okay, and then there are also other gate capacitances like between gate and source terminal, gate and drain terminal. Okay, so the effect of those capacitances has never been included in the AC equivalent circuits or any small signal regime operations of transistors. So it turns out that these capacitances are very much effective in determining the amplifier frequency response. So in this video, we are going to see how these capacitances are going to affect the amplifier frequency response, and in general, any large signal operation of transistors such as in digital logics, you cannot assume that these capacitances get instantaneously charged, and because practically there is a propagation delay even in digital circuits or transistor logic based circuits, and this is due to these capacitances. So let's consider these capacitances separately, the effect of these capacitances separately. So to start with, you see all the amplifier gain factors are functions of signal frequency, and these gain factors, they include the voltage gain, current gain, transconductance gain, and the trans resistance gains. Okay, so up to this point we have assumed that the signal frequency is high enough so that the coupling and the bypass capacitors can be treated as short circuits, and at the same time we have assumed that the signal frequency is low enough such that the parasitic, load, and the transistors internal capacitances can be treated as open circuits. You see, now there are two different groups of capacitances. One is the transistor capacitances, okay, which are internal capacitances such as between the junction source and the body, the drain and the body, the diffusion of charges. There could be reverse p-n junction capacitances. Then there's another set of capacitances which are external in the configuration of transistor as an amplifier. Those are the bypass capacitors, coupling capacitors. So we have assumed that these bypass capacitors and the coupling capacitors are short circuits, so we have not included their effects in the linear regime operations of transistors and amplifiers. Similarly, the transistor internal capacitances, for transistor internal capacitances, we have assumed that the signal frequency is low enough so those capacitances can be the capacitive reactance can be taken up as an open circuits. Okay, so we don't consider the fact of these two group of capacitances in any general amplifier configuration. So in general, an amplifier gain factor versus frequency will resemble that shown in the figure below. So you see both the gain factor and frequency are plotted on logarithmic scales. The gain factor is in terms of decibels. So you see in this figure down below, we have an amplifier gain versus frequency, and this is the function of frequency in decibels. Okay, this is versus frequency. This is the logarithm scale, and you see over here there are three regions. One is the low frequency region. Okay, then you have the mid-band region where the gain is independent of frequency. It's not changing with as the frequency is increasing. There is no change in the voltage gain. Then you have the high frequency range. Okay, so that's the point. Both the high frequency and the low frequency are the points where the mid-band gain falls 3 dB below. Okay, 3 dB below the maximum gain, which is noted by AM dB. Okay, AM is the mid-band gain, and the range of frequencies, the bandwidth that is contained, that contains the frequencies is the difference between these two frequencies. So this is the bandwidth of the amplifier. This is the bandwidth of the amplifier. So that's the bandwidth that we are interested in design of an amplifier, where these capacitances are not going to affect, for example, the voltage gain of the amplifier. The voltage gain is independent of the frequencies in this range. So that's the bandwidth of operation. You don't want the amplifier gain, for example, to decrease as the frequency decreases in low frequency range. Similarly, you don't want to operate there at very high frequencies where the response or the voltage gain again tends to decrease. Okay, so if you have to design somewhere, for example, if it is an audio amplifier, then it has to operate within 20 hertz to 20 kilohertz. So that should be within the bandwidth within FH minus FL. So 20 kilohertz should be below FH and 20 hertz should be above FL, so that audio amplification can be done within the bandwidth of the, for example, linear audio amplifier. Okay, so these you see three frequency ranges: low, mid band, and high are indicated in this figure. In the low frequency range, where the frequency is less than FL, which is 3 dB, is the point that is 3 dB below your midband gain. This happens to be the midband gain, that's constant. Similarly, you have another point, FH, which is again 3 dB below. So the gain is decreasing in this low frequency range, decreases because of the coupling and bypass capacitor effects. So as the frequency is decreasing, your coupling and bypass capacitor effects, they come into the picture, and they cause the decrease in the frequency response. Okay, but for high frequency, where once again as the frequency is increasing, the midband gain falls 3 dB below. So at this point, the response that is decreasing is due to the internal capacitances of the transistor. Okay, so this part is because of the internal capacitances of the transistors. So let's write this as internal, actually the internal transistor, internal FET capacitances. Okay, and in the low frequency range, the capacitances that are causing the decrease in the gain are due to the, for example, bypass capacitors and the coupling capacitors, CC. Okay, so these are the capacitors that are causing the decrease in the frequency. Okay, you see the capacitive reactance is given as 1 over 2 pi FC. Okay, so the capacitive reactance is a function of frequency itself. So as the frequency is decreasing, the capacitive reactance is increasing. So you cannot ignore their effect at very low frequencies. For example, I mean, and similarly at very large frequencies, the capacitive reactance is small. So the effects are going to be, you have to include their effects, okay, outside the bandwidth of the operation of the transistor. Okay, so in the high frequency range, when F is greater than FH, the state capacitances and the transistor capacitance effects, they cause the gain to decrease as the frequency increases. So again, you see for the high frequency range, that is above FH, okay, above FH, the capacitances that are responsible for the decrease of the midband gain are the internal and the stray capacitances of the, especially related to the transistors. Okay, those are internal capacitances. And for the low range frequency, we have the bypass and the coupling capacitor that are the external to the transistor. Okay, the midband range is a region where the coupling and the bypass capacitors they act as short circuits, and stray and transistor capacitances they act as open circuits. So in this region, the gain is almost constant, as we'll show that the gain at F is equal to FL and F is equal to FH, that's the high frequency point and the low frequency point, is 3 dB less than the maximum midband gain, that is AM. Okay, so that's 3 dB, both the points are 3 dB below the midband gain, which is given by AM dBs. So the bandwidth, okay, the bandwidth of the amplifier in hertz is given as FBW bandwidth, which is FH minus FL. That's the 3 dB bandwidth of the amplifier. That's the bandwidth within which the frequency response stays within 3 dBs. Okay. So for an audio amplifier, for example, the signal frequencies are in the range of 20 hertz, 20 kilohertz, and that need to be amplified equally so as to reproduce the sound as accurately as possible. So for that, you have to design the audio amplifier such that FL must be designed to be less than 20 hertz, okay, and FH must be designed to be greater than 20 kilohertz. So your audio frequency stays within the midband range, where the gain is not depending on the stray capacitances and transistor capacitances and the capacitances which are external to the transistors, such as coupling and bypass capacitances. Okay, so to provide a gain which is independent of frequency, you have to design your transistor such that for audio amplification, 20 to 20 kilohertz is within the bandwidth of the midband range. Okay, All right, now based on these ranges, we have the equivalent circuit. So each capacitor in a circuit is important at only one end of the frequency spectrum. So for this reason, we can develop specific equivalent circuits that apply to the low frequency range, to mid-band, and to the high frequency range. So for the mid-band range, I mean, up until now, I think all of these circuits that we have considered in developing the small signal, for example, circuits for common source follower, common gate configurations, we have not considered any capacitances. So mid-band range is independent of the capacitive effects. So these equivalent circuits used for calculations in mid-band range are the same as those considered up to this point in the text. So as already mentioned, the coupling and bypass capacitors in this region are treated as short circuits. Those are external capacitances. The stray and transistor capacitances are treated as open circuits. So in this frequency range, there are no capacitances in the equivalent circuit. So all the small signal or the large signal AC equivalent circuits that we have considered, we have not considered the effect of the stray capacitances and the external capacitances. So these circuits are referred to as mid-band equivalent circuits. So whenever you see the mid-band equivalent circuits, those are circuits that don't include the effect of such capacitances in the frequency, because the frequency response happens to be independent of such capacitive effects, and it's independent of the frequency. Okay, the gain stays constant. The gain stays constant. So we are not going to include any effect of capacitance in the mid-band range. Okay. All right. So for the low frequency range, in this frequency range, we use a low frequency equivalent circuit, and in this region, the coupling and the bypass capacitors, they must be included in the equivalent circuit and the amplification factor equations, because they're going to affect your gain. The gain is not independent of frequency. Instead, it becomes a function of frequency, which decreases as frequency decreases. Okay, so the gain is decreasing with the function of frequency. So you have to include the external capacitances in the low frequency range. So the stray and the transistor capacitances are treated as open circuits in this range. The mathematical expressions obtained for the amplification factor in this frequency range, they must approach to the mid-band results as f approaches to the mid-band frequency range, since in this limit the capacitor approaches the short circuit conditions. So what it means is that for this range, for this low range, you have to consider the bypass and the coupling capacitors in your equivalent circuit. But the equivalent circuit, the equivalent AC circuit for example, for large signal regime, or if you're considering a linear circuit or small signal circuits for linear amplification of small signals, you have to include the effect such that when you approach your low frequency point, FL, the circuit, response of the circuit before reaching the mid-band should exclude the effect of bypass and coupling capacitors, okay? Because these capacitors will now act as short circuits in the mid-band equivalent circuits. Okay, mid-band is not going to include either transistor capacitances because they are open, and the bypass and the coupling are short. Okay, so in the mid-band, the bypass and the coupling capacitor, they should be shorting out. Okay, because as the frequency is increasing, the capacitive reactance is going to decrease. Okay, so so the effect should be such that bypass and coupling capacitors become short circuits. Okay. Similarly, in the high frequency range, we use high frequency equivalent circuits. That in this region, the coupling and bypass capacitors, they are already being treated as short circuits. The transistor and any parasitic load capacitance must be taken into account into this equivalent circuit. And the mathematical expressions developed obtained for the amplification factor in this range, they must approach the mid-band result as f approaches the mid-band frequency range, since in the limit the capacitors approach open circuit conditions. Okay, so if you are around fh, again 3 dB below your mid-band gain, then in this range your stray capacitances and your transistor capacitances, they should be considered as open circuits. So in all the mathematical expression, transfer functions, for example, frequency responses, as the frequency is around fh, the stray capacitances and transistor capacitances should be excluded. Okay, their effect should be excluded. Then, well, how do we analyze the frequency response? So using these three equivalent circuits, just considered rather, then a complete circuit is an approximation technique that produces useful hand analysis result while avoiding complex transfer functions. So this technique is valid if there is a large separation between FL and FH. That means the bandwidth of the operation is large, or the midband region is large. So this condition is satisfied in many electronic circuits that we shall consider. Now, computer simulations such as PSpice can take into account all the capacitances and can produce the frequency response curves that are more accurate than hand analysis results. But however, these computers, they do not provide any physical insight into a particular result, and hence don't provide any suggestion as to the design changes that can be made into the particular frequency response. Okay, so if you're going to, for example, simulate your circuit, you're going to do the transient analysis or the linear circuit analysis with all these capacitances. Computer is going to give you the frequency response, but to provide an insight to why and where of, you have to change your circuit according to meet the design requirements. For example, there's no insight into these results. So to have a better insight, you must be able to, for example, do the hand analysis. You should be able to understand the mathematical expression or the transfer functions behind the circuits that should relate the input and output voltages in order to be able to understand the operating characteristics of the transistors and to make the necessary changes to meet the design requirements. Okay, so a hand analysis can provide insight into why and where-offs of the particular response. So this basic understanding can then lead to a better circuit design. The derivation of these mathematical expressions relate the output voltages to the input voltage. So this is known as transfer function as a function of signal frequency. From these functions, we can further develop the response curves. These two the two frequency responses curves are the magnitude of the transfer function versus the frequency, and then the second one is the phase of the transfer function, because you understand that the analysis is generally complex, so it's going to include both the magnitude and the phase or relating the input and output voltages. So for example, the phase response relates the phase of the output signal that of the input signal. Okay, so a hand analysis, for example, if you can come up with the transfer function of the transistor circuit, then you can see how the response or the behavior of the circuit will be as a function of frequency. When the frequency approaches FH, or if it goes to around FL, then how these capacitive effects can be taken into account, and how the circuit can be designed within the midband range, where your gain factors, current gains, voltage gains are independent of frequency. Okay, so it gives a very better insight for the design of the circuit. Okay. Okay, so let's talk about before we develop the circuits with including those capacitances in the small signal model of the MOSFET. Let's first discuss the MOSFET internal capacitances, and then we shall develop a high frequency model with these capacitances. So now, from our study of the physical operation of MOSFET, if you recall, we know that this device has internal capacitances. So in fact, we use one of these, and that was the gate to channel capacitance in our derivation of MOSFET IV characteristics. Now, if you recall in our earlier discussion of MOSFET construction, it's primarily a 4-terminal device with the substrate and the source are usually tied together. So, and they both are connected with the most negative, which is the common of the circuit. So you don't see the bulk or the substrate terminal. Then you have the VGS, so it's basically a 3-terminal device. Then you have the source, then you have the gate, and then you have the drain terminal. Okay, so one capacitance that we have already considered is between the gate, which is either polysilicon material or it's a metal. Okay, so that metal is separated from the semiconductor, P-type semiconductor, let's say for NMOS device, by the oxide, which is of thickness 2x. Okay, so this capacitance, we already considered this capacitance to be open circuits in the small signal operations, and this is one of the internal capacitances of the transistors. Okay, so we have already mentioned about this, and this capacitance, you'll see that is dependent on the length of the channel and the width, those are the dimension parameters of the channel. Once VGS becomes greater than the threshold voltage, the transistor starts to conduct, and there is a formation of channel. So from where the source, after which the charges starts to travel from source to drain terminal, and the current flows in the device. So there's already a capacitance, so you're already creating a field between gate and the source terminal, or the gate and the body terminal. Okay, so we already know about this capacitance. So we did, however, implicitly assume that the steady state charges on these capacitances are acquired instantaneously. That was also another assumption. Besides the open circuit transistor capacitances, we assume that the steady state charges on these capacitors are almost acquired instantaneously. In other words, we did not account for a finite time required to charge and discharge the various internal capacitances. Okay, so for a capacitor, which is, for example, discharging across the load, which is charged up initially, requires a certain time. There's a term like known as time constant, for which the capacitor discharge across the load. We have not considered those times. Okay, so as a result, the device models that we have derived, such as the small signal model, do not include any such capacitances, and the use of these models would predict the constant amplifier gains independent of frequency. So we know, however, that this is unfortunately not the case. In fact, the gain of every MOSFET amplifier falls off at some high frequency. So similarly, the MOSFET digital logic inverter exhibits finite non-zero propagation delay, and that finite propagation delay is due to the finite time constants of these capacitances. Okay, so to be able to predict these results, MOSFET model must be augmented, including the internal capacitance. So we must include these internal capacitances. So let's first introduce ourselves to these internal capacitances of the MOSFET. So there are basically two types of internal capacitance in the MOSFET. One is the gate capacitive effect. So between the gate and the other terminal, for example, you have between, this is gate terminal, this is source, drain. So between all these three terminals shown besides the gate, so this is, let's take this as the body terminal. If let's say body and your substrate, if they are not at the same potential, you recall that there was a body effect, and that due to that body effect, you have to model this by a back transconductance gain, and there's another current source that has to be included in the model. Okay, so if the source and the bulk or the body is not at the same potential, then if there is let's say VSB, which is positive, okay, it's a positive potential, then there is another current source besides VGS. So instead of GM-VGS, you have GMB-VSB, which models the current in small signal models due to the bulk effect, okay, body effect, which the source and bulk are not at the same potential. Anyways, over here, you see that instead of gate, we have three other terminals. So do you have the capacitances between these three terminals? So there's a capacitance gate source, and there is a gate to drain capacitance, and then there is a gate to bulk capacitance. Why these capacitances are there? Because of, in between these all three terminals, there will exist a potential difference. When there is a potential difference between two terminals, two metallic terminals, there is capacitances. Okay, there is a capacitive effect because of the establishment of the field. Okay, so the first is the gate electrode, which is either polysilicon or metal. So it forms a parallel plate capacitor with the channel. So with the oxide layer serving as the capacitor dielectric. So this dielectric has a thickness of TOX, which is the oxide. Usually it's the oxide that's the dielectric between the gate and the channel. That's the first capacitance. Then the second internal capacitance are the source body, drain body, depletion layer capacitances. So you will have, besides the terminal capacitances, you're going to have internal capacitance. For example, this is P-N junction, and this is reverse biased. Okay, so for example, if you're going to apply a positive source over here, a positive battery source to the drain terminal over here. So okay, positive. For example, this is your VDS, and this is reverse bias. This is N-doped region. So this is again PN. So this becomes reverse bias. There is a capacitance. Okay, there's a capacitance built up, and this is called the diffusion capacitance. So these reverse biased PN junctions over here, and the source and drain. So the source and bulk the source and the P-type body, uh, reverse bias PN junction, and the reverse bias PN junction between drain and body is going to have another capacitance that is internal to the transistors. So these are the capacitances of the reverse bias PN junctions formed by the AND source region, also known as source diffusion, and the P-type substrate, and then there is AND drain region, and the drain diffusion and the substrate. Okay, so we have two types of capacitances, that is between the terminals, and that's the first one. So between the gate and source, so between the gate and drain, gate and body, and then we have the internal capacitances. Those are the capacitances due to the reverse PN junctions of source and drain terminal. Okay, and those are between source and the body, and the drain and the body. So these two capacitive effects can be modeled by including capacitances in the MOSFET model between its four terminals. That's the gate, drain, source, and bulk. Okay, so we are assuming the source and the body are not at the same potential over here. So in that case, there will be 5 capacitances in total, given the 4 terminals. So those are gate source, okay, between the gate and source, then there is between gate and drain, and between the gate and bulk, then you have between source and bulk, okay, because they're not at the same. If source and bulk were connected together, then you don't need to consider CSB. Because they're the same potential, so there is no field between CSB. Then you have between the drain and bulk. Okay, so now these subscripts indicate the location of these capacitances in the model. So let's see the model how these capacitances can be connected. Okay, so there is some relationship first that are given for the gate capacitive effects. For example, the gate capacitive effect can be modeled by 3 capacitances: CGS, CGD, and CGB. Those are the gate 3 capacitances, 3 gate capacitances. The value of these capacitances can be determined as follows, and these are all approximations. That's how it's done in the modeling. Okay, so when MOSFET is operating in, for example, non-saturation region, when there is a small VDS, the channel will be of uniform depth. Okay, it's not going to be tapered off from the drain. For example, what happened at the for example, pinch off voltage in FETs, or for example, what happens after the transition point, once the saturation point is reached. After that, VDS is not effective in affecting the drain current. So we say that the channel is pinched off at the drain, so there is tapering off. But as far as VDS is small, as long as VDS is small, the channel is of uniform depth. Okay, so we say that the channel is not tapered off. It's for small VDS. It's quite the length is uniform. Okay, it only happens when you increase VDS, so that this becomes so much reverse biased. The channel becomes tapered over, so it pinches off over here. So channel becomes like this instead. So that's the point where you don't need to consider, for example, the capacitance at the drain terminal, okay, because the channel is pinched off. So anyways, when VDS is small, the gate channel capacitance will be the area of the channel, that is the width and into the length, multiplied by CUX. CUX is the parallel plate capacitance, gate capacitance, and with the oxide as the dielectric, and WL are the respectively. This is the width of the gate, and then you have the length of the channel. It's a rectangular region, so W by L is the area. Okay, and if you recall, CUX is the capacitance per unit area, so WL CUX is in farads. It's capacitance, and it can be modeled by dividing it equally between the source and drain ends, because your channel is uniform. So between the source and drain, you can the capacitances are equal. It's given by half of WL CUX. Okay, so these capacitances are divided equally between the source and drain terminals, and this is valid. This expression is modeled in non-saturation region, and VDS is less than VDS sat. Okay, so this expression is for VDS less than VDS sat. So that is before we reach the saturation region, or say that we are in the triode region. So that's the case. Then you see, this is an obviously an approximation, as all modeling is. All modeling is approximation, but works well for the triode region. operation, even when VDS is not as small. It has to be less than VDS sat. Okay. So then when MOSFET operates in saturation, the channel has a tapered shape and is pinched off near the drain end. So the situation is like this. As VDS, you go on increasing VDS, what happens is that your channel, your depletion width is going to increase because you're putting a positive charge over here. This is negatively doped region. So you're going to create a reverse bias at the drain, and the depletion region is going to increase. Therefore, it's going to pinch off the channel at the drain. So as an effect of that, it can be shown that the gate to channel capacitance in this case is 2/3, okay, CUX. So that can be modeled by assigning the entire amount to CGS and 0 to CGD, because the channel is pinched off at the drain. So you see the gate capacitance between the gate and drain, the channel is pinched off. We don't have any capacitance, okay. The drain terminal is pinched off, but between gate and source, this is 2/3 of the total gate capacitance. So between gate and source, you have 2/3 of the gate and channel capacitance, okay, where the gate channel capacitance is WLCOX. Then when MOSFET is in cutoff, the channel disappears. You don't have any channel, so there is no conduction between source and drain, and therefore CGS and CGD are 0, right? So since they are not conducting, you're not putting up any supply on the drain terminal, or either there is no potential at the source. So basically there is no capacitance that forms. So we can, after some rather complex reasoning, model that the gate capacitive effect by assigning capacitance WLCOX to the gate body model capacitance. So thus you see we don't have any capacitance assigned between gate source and gate drain, but we have the capacitance between gate and the bulk or the body, and that's the entire capacitance WLCOX, which we can assign between the gate and the body terminal, okay. So we're not assuming that over here the source is connected to the bulk. If source and bulk are at the same potential, if Vs is equal to Vb, well, in that case your CGB is also 0. This will also be 0, okay. But however, this is not the case over here. So therefore, all the capacitance, the gate capacitance, the gate capacitive effect is assigned to the gate body capacitance model, okay. So number 4, there is an additional small capacitive component that should be added to CGS and CGD in all the preceding formulas. This is the capacitance that results from the fact that the source and drain diffusions, they extend slightly under the oxide, okay. So why these diffusions are extending, that's because of the reverse bias PN junctions. So if the, for example, overlap length is denoted by LOV, we see that this overlap capacitance is given as, so this overlap length could be 5 or 10% of the channel length, for example. Over here typically this is 5 to 10%, and it's given by WLOV-CUX, so which is again very small capacitance that should be included to CGD and CGS models. So for example, if your source is going to be reverse biased over here, this also increases, and there is small overlap. So for example, this is the overlap. So if it's going to come under the channel, then this is your LOV, that's the overlap length. And you have to include this length because the field effect is also being established due to this length, okay. So for example, the overlap length in both drain and source regions, you have to include the effect between gate source and gate drain capacitance, okay. All right. So we have this capacitance between the gate and the other terminals. Then comes the purely internal capacitances. Those are the junction capacitances. For example, these junction capacitances are, if you recall, are the PN junction capacitances, which are reverse bias in both the source and the drain. So the depletion layer capacitances of the 2 reverse bias PN junctions formed between each of the source and drain diffusions and the body can be determined using the following expressions. So thus for the source diffusion, we have the source body capacitance CSB, okay, where in this expression CSB naught is the value of CSB at zero body source. Okay, that means that's the capacitance. Well, it should be the case because you see, if you substitute VSB equal to 0, that is source and bulk, which are usually tied up together to the most negative or the common ground. If the potential difference is 0, then CSB is nothing but CSB naught. Okay, so that means when your source and bulk are tied up together, and that's the common ground of the circuit. So if CSB naught is the value of CSB at zero body source bias, and VSB is the magnitude of the reverse bias voltage. Similarly, V naught is the junction built-in voltage, which is intrinsic. It's about 0.6 volt to 0.8 volts of the junction. Similarly, for the drain diffusion, we have the drain body capacitance, CDB. Again, this is only when VDB is greater than 0. Okay, so this only occurs when VDB is not equal to 0. So, and well, usually we don't have CSB. We don't have CSB in practical circuits, but we do have a small CDB. Okay, although not significant, but we have CDB. Okay, CSB is usually 0, but CDB has to be included. So CDB naught is when VDB is 0. So CDB naught is the capacitance value at 0 reverse bias voltage. So when VDS is not there, for example, when you don't have any VDS, CDB is CDB naught. VDB is the magnitude of the reverse bias voltage, again of the same order. Then, okay, so note that we have assumed that for both junctions, the grading coefficient is half. Usually the grading coefficient measures the profile of semiconductor doping. Okay, so for example, for abrupt junction dopings, it's usually 0.5. For linear doping profiles, for linear junctions, it's about 0.33, which is taken in simulations. Basically, it has to do with the doping profile of the junction. Okay. All right. So it should be noted also that each of these junctions capacitances, they include a component arising from the bottom side of the diffusion and a component arising from the side wall of the diffusion. You see, well, it's all modeling work, but you have to understand that there are gate capacitances and then there are diffusion capacitances. So, for example, in this figure, there are side walls as well. Okay, so there's going to be a capacitance. It's not this PN junction, but there's going to be a capacitive effect from the side walls as well, from the side wall at both the drain and the source terminals. Okay, also you're going to have some effect from the channel side as well. So there's going to be capacitances from the sides as well. That's how the construction is. So in this regard, we observe that each diffusion has 3 side walls that are in contact with the substrate and thus contribute to the junction capacitance as well. The 4th wall is in contact with the channel. So in more advanced MOSFET modeling, the 2 components of each of these junction capacitances are calculated separately. The formulas for the junction capacitances assume small signal operations. So these formulas, they assume the small signal operations, but both of these formulations are for small signal operations. They're not for large signal operations. So if you have to consider the full-blown operation or large signal operation of transistor, for example, like in digital inverter circuits, you have to consider more involved expressions. So these formulas can be modified to obtain approximate values, average values for the capacitance when transistors operating under large signal conditions, such as in logic circuits. Okay, so let's try to construct a high frequency model for a common source MOSFET model. So over here you see we have a common source basically, and over here the other thing that you should notice, because we are applying the signal at VG. Okay, that's your input signal at the gate, and the output is being taken from the drain. And one more thing that you should notice is that the potential of Vs is not the same as the bulk potential, the body potential. Okay, so there is a difference. So due to positive VBS, okay, due to positive VBS, we are going to have another. This is known as the bulk effect or the body effect. To that, we are going to have another current component in the, which you can see over here in the model of the common source MOSFET circuit. And then besides GMVGS, which we have the transconductance gain, is the generic transconductance gain of the MOSFET. in terms of the Q point parameters, the conduction parameter, and the drain current at where the transistor is biased. We have this GMB VBS. GMB is the back transconductance gain. Okay, so we've already talked about this in details in previous videos. If you go there and have a look, GMB model is the back transconductance gain, and that only occurs when the bulk and the source are at different potentials. Okay. Otherwise, we haven't considered this CSB. CSB would have been 0 if the bulk and source are tied together, and then this VBS is also 0, so you don't have to consider this. So circuit simplifies a lot. Okay, in that case. Anyways, so in this circuit, you also see that we are considering this gate and drain capacitance. So between gate and drain terminal, you are going to have your CGD. Between gate and source, you're going to have CGS. Okay, and then between drain and bulk, you have CDB, and you have CSB between source and the bulk. This is the source terminal, okay, and this is the body terminal. So we are considering 4 such capacitances in this model. Okay, so this is a pretty complicated model to analyze by hand. It's not that straightforward. So this figure below, you can see this is the small signal model of MOSFET, now which includes the 4 capacitances, CGS, CGD, and CSB, CDB. This model can be used to predict the high frequency response of MOSFET amplifiers. It is, however, quite complex for manual analysis, but its use is limited then to the computer simulations. For example, SPICE, you can go ahead and using PSPICE or LDSPICE and run the transit analysis, but for hand analysis, it's not that straightforward to relate the input and output voltages by a simple transfer function. So fortunately, for the case when the source is connected to the body, the model simplifies considerably, and that's shown in figure B. So this is the high frequency model that consists of all the capacitances, with the source and the body are not tied when they are not tied together. But when they become tied together, then in figure B, okay, figure B is on the next slide, when source and body are tied up together, and you don't see any other bulk terminal. So the capacitance between source and bulk, it vanishes. Okay, so that capacitance is gone, and you're left with 3 capacitances. Okay, before that we have 4 capacitances. So this capacitance over here has vanished. Okay, so CSB is vanished, and then we are left with CGS, CSD, CDB. So that's still there. Okay. However, in part C, it's still a much simpler simplification. So part B is when the equivalent circuit for the case in which the source is connected to the substrate. The other thing that you have noticed is there is no other current source due to VBS. Okay, that's also gone. So in part C, the equivalent circuit of part B with CDB neglected to simplify the analysis. So if you are going to neglect this capacitance over here as well, it's going to much simplify the analysis of the circuit. So this circuit can be analyzed easily by manual analysis, writing the KVL and K-scale output-input equations, and then you can write a transfer function relating the output voltage to the input voltage. Okay, so the transfer function of the form Ts, where S is the complex frequency variable, will relate the output voltage, small signal output voltage V0 by input voltage, for example. Okay, which is over here in this case VGS. Okay, that's the input voltage. Output voltage is being taken from the drain. Okay, so in this model, CGD, although small, plays a significant role in determining the high frequency response. So CGD is supposed to be there. We have kept that throughout of the amplifiers and must be kept in the model. Then the capacitance CDB, on the other hand, can usually be neglected, resulting in significant simplification of manual analysis. The resulting is figure C. So we have not considered CDB over here, and we are only left with the CGD and CGS. So if you recall in the previous circuits, we have not even considered CGD and CGS. Okay, so that was left open. We were leaving the internal gate capacitances of the MOSFET as open circuits. Okay, so between G and S there is no capacitance. R0 is due to the channel-based modulation parameter, lambda if it's there. So you have to include the output resistance between drain and source of the MOSFET, and that's internal to the MOSFET. It's not the external resistance. And then you have to consider the transconductance gain, which is a small signal parameter, multiplied by the VGS, which is the input signal. Okay. So this circuit is quite simplified. Part C is a very simplified circuit which we can consider for the frequency response analysis. All right. So now one important figure of merit for MOSFET is the unity gain frequency, FT. This is the figure of merit for the high frequency operation of MOSFET as an amplifier in the unity gain frequency. So what it means is that if you short out the output, okay, then the short circuit current I0 relating to the input current II has to be independent of frequency. So this is defined as the frequency at which the short circuit current gain of the common source configuration becomes unity. So it's not dependent on the frequency. So the current gain, again, the current gain at which the short circuit current gain of the common source configuration becomes unity is your unity gain frequency FT. Okay, and usually it's very large in typical 5 micrometer or 0.13 micrometer CMOS technology. It has to be very high. So figure below shows the MOSFET's hybrid pi model, and in that you see we are not including CDB, okay, and bulk and source are at the same potential. This is your source terminal, okay. This is your gate terminal. The output is shorted out, okay. So in this model, source is common, so it's a common source configuration. It's again a common source configuration, and most common source configuration. So source is common between your input and the output. That can be seen from this configuration. You're applying the input at the gate, and the output is shorted out. So to determine the short circuit current gain, the input is fed with a constant current signal II, and the output terminals are shorted. So it is easy to see that the current in the short circuit is given by, so if you apply the KCL over here, so this resistance is basically shorted out. So what you have is I0. You can write this as by applying KCL at this node. Okay, this is the short circuit current becomes GMVGS with the transconductance gain and the input signal minus S is the complex frequency variable, okay, as CGD VGS. Okay, so this is this capacitance. Okay, so basically the capacitive reactance is SCGD. So because the capacitive reactance is of the form, you can write this as the current the current through CGD is okay. You have to take the ratio of it's basically VGS divided by 1 over CGD. Okay, so this comes in the numerator with the VGS. Okay, so recalling that CGD is small, at the frequencies of interest, the second term in this equation can be neglected. So therefore, an approximation is that the output current is about GMVGS. Okay. So this is the output current. This is the output current as an approximation when your CGD is small. So you can assume that this is a small term. You can ignore the second term. So we can express VGS in terms of the input current II. Okay. VGS over here. This is your VGS over here. This is VGS. This should be VGD basically. This should be VGD. Okay, so we are talking of this capacitance. So basically, this is VGD divided by 1 over SCGD. That's why your SCGD term is coming with VGD, not VGS, because GD is small. So you can ignore that. Okay, you can ignore that. So even if you consider R naught to be very large, you can consider that to be open circuit. Then it's very easy to see. If you consider that as an open circuit, then I naught is basically at this point. This is your I naught. Okay, so I naught, if I naught is equal to GMVGS, okay, then minus because the current flows over here as well, and that's here. So this is VGD over 1 over SGD, and SGD is, CGD is small. Just ignore the second term, and you're left with I naught as GM/VGS. Okay. Similarly, the input current over here, you can see if you apply the KCL over here, the current in this branch is what? VGS divided by S, VGS into S, CGS is your current to this branch, so this capacitance between gate and source. So the input current and written in terms of VGS as VGS is equal to II over S CGS plus CGD. Okay, so there will be current that's going to bifurcate in this branch, and that's also coming in this branch as well. So you can, if you write the expressions for collect the currents in both these branches and write this in terms of II from KCL, that's the expression for the input current. And considering the output current, this equation, the output current and the input current, you can take the ratio, so the short circuit current gain becomes I naught over I as GM SCGS plus CGD. So so again, you see this current gain is directly proportional to the transconductance gain of the amplifier. Okay, and it's inversely proportional to the gate source capacitance and the capacitance between the gate and drain terminals. All right, so you can see why this gate to drain terminal capacitance is important, because it's going to affect the frequency response of the current gain. So for short circuit current gain, so for physical frequencies as is j omega, it can be seen that the magnitude of the current gain becomes unity at the frequency. Okay. So if you're going to replace S by j omega over here, the omega becomes GM over CGS with CGD, and then you can obtain the unity gain frequency as dividing by the same expression by 2 pi over here, gives you the unity gain frequency Ft. So since Ft over here is again proportional to Gm and inversely proportional to the transistor internal capacitances, so the higher value of Ft, higher the value of Ft, the more effective the transistor becomes as an amplifier. Okay, so typically Ft ranges from about 100 megahertz for older technologies, for example 5 micrometer CMOS processes, to many gigahertz for new high-speed technologies like 0.13 micrometers CMOS processes. Okay, so Ft is your you see the reason for this, again, this Ft is the frequency for which the current gain is unity. Okay, so if you replace over here, since S is j omega, okay, S is j omega, and if you're going to replace omega such that Ft and omega is a relationship, there is a 2 pi, okay, 2 pi F is omega. So Ft is, if you're going to substitute this for omega, let's put omega itself. So if omega is equal to Gm over CGS plus CGD, CGS plus CGD, then the current gain is unity. Okay, the magnitude of the current gain becomes unity. Under these conditions, the magnitude of current gain becomes unity in these conditions. So that's your that's why this Ft is called the unity gain frequency of the MOSFET amplifier. And again, you see, considering these capacitances, the gate to drain is very important over here. That determines the frequency at which the response stays unity. Okay. All right, that's all.